And good morning, everyone, and welcome to another one of our fleet seminars. I'd like to begin by acknowledging the traditional custodians of the land from which this talk is being presented and from which many of us are watching these talks spread across Australia. So it's a great pleasure to introduce Dr. Feixiang Xiang. Feixiang did his PhD and Masters at the University of Wollongong under the supervision of Professor Du and Professor Xiaolin Wang. And he did some pioneering work on tungsten ditelluride, which many of you know is a 2D transition metal dichalcogenide, which has some very interesting and exotic properties. Since 2017, he has moved to the University of New South Wales, where he's a member of the New South Wales Node of Fleet, and has done some beautiful experiments on graphene-based van der Waals heterostructures. So it's a great pleasure to introduce Feixiang and to catch up on some of his latest research.
Yeah, okay, thanks, Alex. Good morning, everyone. So I'm Feixiang. I'm currently a postdoc research fellow in Alex Hamilton's group at UNSW. Thanks Sue as well for organizing this free seminar so that I have a chance to talk about my recent works on exploring new quantum phenomena in graphene-based van der Waals heterostructures. So the first part of my talk will be the double moiré superlattice in HPM encapsulated graphene van der Waals heterostructures. So during the advance on fabrication of graphene moiré superlattices offers a great opportunity to engineer band structures of graphene, and many exotic quantum phenomena has been observed in graphene after the band engineering, such as secondary cone and Hofstadter butterfly, and also the correlated insulating states and superconductivity, even the quantum anomalous Hall effect. So how to create a moiré superlattice? One way we can do is by stacking two same 2D material and on top of each other, and by slightly twist them, and there will be a moiré pattern formed. And the moiré pattern shows like a very long periodicity, and can modify the band structure. So alternatively, moiré superlattice can be created by stacking two different 2D materials, but with the same crystal structure, but with a slightly different less constant. The periodicity of the moiré superlattice in this case can be further tuned by the twist angle. So one special interesting band structure engineered by the moiré superlattice is the flat bands, whose band width is very narrow, and the density is very high. A typical example of such a moiré superlattice is a magic angle twist bilayer graphene, where the two graphene flakes are stacked with a very small angle around 1.1 degree or 1.08 degree more precisely. the way of the fiber band generated in the twist bilayer graphene is believes that the interrail hybridization between the two graphene layers makes the two direct cones, and the magic angle renormalize the Fermi velocity and open a gap near the crossing of the cone. As a result, very flat band with bandwidth about 10 millieV it formed near the low energy regime. The other case is where a very flat band observed is the ABC stacking parallel graphene aligned to the aligned with the HBM. In this case, the flat band result from in a different mechanism because the ABC stacked parallel graphene, the band structure is very flat at the low energy regime, and the super lattice can create can open a gap and isolate a midi band by further tuning the electric field across the sample. The gap, I mean the original band sort of crossing point at zero energy is also opened, and there will be a very flat band on the whole side. So the question is, are there other ways to create a flat band in the graphene-based moiré heat structures? So recent work from James Home Group shows that if the graphene monolayer graphene flake is aligned to to the top and bottom HBM, but with a very small twist angle, two super lattice, two moiré super lattice can form at the bottom and top of the graphene flake, and these two these two super lattice can near the band structure of graphene, and when they measure the resistivity as a function carrier density, they see two insulating state from the top and bottom moiré super lattice. So they propose if these two gap are very close to each other, there's possibility the band, this isolated band is very narrow and can promote the sort of correlated states and other new quantum phenomenon. So how do we? We follow this idea and prepare some like a double double moiré graphene band Waals heat structures. So how we prepare such a sample? So we basically align the crystal orientation of different graphene between graphene and HBM flex. The unique thing is, or the feature we use is that when the graphene or HBM being exported from bulk crystal, the flex shows the zigzag edge or the armature edge. In the optical image or like or the SEM image, we can see very long edges so like this we these crystals or flex we exfoliate, we found very long edge for this top HBM and this monolayer. There are few very long edges, and then we align them and align them so this is the final stack, and this is shows a schematic diagram how these three flex are stacked. So this figure shows the schematic diagram, and we use E-beam lithography and dry etching to etch down the stack into whole bar structure for transport measurement. So we first calculate the capacitance by recording the from the whole measurement at a fixed magnetic field, and then super the backgate voltage, and from this slope we can estimate the gate capacitance, which is about 12.0 nanofarad per square centimeter. Then we estimated the mobility from the zero magnetic field transporter. So this diagram this figure shows the conductivity as a function of carrier density, and using this equation we can estimate the mobility. On the electron side, the mobility is about 90,000. On the host side, the mobility is slightly lower, smaller. Yeah, it's about 72,000 centimeter square per volt per second. So the mobility is quite high, and indicated sample quality is very good. And then we try to probe the signature of the double moiré super lattice. So we measure the resistance as a function of gate voltage. So normally for graphene, we can see one of resistance peak at charging point. But in this case, we can see some like a satellite peaks at both electron side and host side, and we can notice there are two peaks on the electron side, but for the host side, there's a dominant peak, but there's a shoulder. So these are the sort of the signature of the two moiré lattice formed at the top and bottom of graphene surfaces. And the moiré sublattice can be further sort of confirmed by the whole resistance, where we see the sign of the XY, the horizons change the sign twice here and near the secondary direct points, and also here as well. So then we estimate because we know get capacitance, then we know the carrier density for where we sort of fulfill the band of the mini band. Then we then we can further estimate the sort of the moiré wavelength. So basically the periodicity of the moiré super lattice by this equation. So we get the periodicity of the moiré wavelength from two moiré superlattice is 11.2 nanometer, and the other one is 30 nanometer. And we can further estimate the twist angle from this equation. And the calculation tells the twist angle is quite small. It's about 0.75 for the first angle, or the 0.4 or 6 degree for the second twist angle. But the thing, I think one thing we can't tell right now is whether we have a plus or minus degree a difference because of the hexagonal crystal structure of HBM and graphene. And one more thing we also notice is these two moiré superlattice further interference with each other and form another super moiré, even larger moiré sort of pattern, where the moiré wavelength is about 31.6 nanometer according to these two calculation. And we compare with the range 2 works, which also observe the double moiré super lattice. In our work, it seems like we observe the two direct points, two secondary direct points are even closer than to previous work. But I think, as I said, so far we can't tell whether we have a plus and or minus 30, 60 degrees sort of offset right now. So we may need to use other technique to tell the to differentiate three different cases. So we also measure the non-Venn diagram, and we can see the Hofstadter butterfly will due to the interference from the Landau label from main direct point and the second direct points, and we can also see very faint double Landau fan come out from the secondary direct point, and also the fan from the super moiré. So this is my first part of my talk. Any questions? Okay, then I'll probably move to no questions. I'll move on to the second talk, second part of my talk. So for this work, I'm recently also present on the Fleet and workshop. It's about the new Landau level crossings and strong electron hole symmetry in Landau level spectrum of bilayer graphene. So the motivation for this work is we try to understand the superfluidity phase in double bilayer graphene sort of quantum wave structure, which is believed to where the high temperature superfluidity can appear. In this because the 2D flex can be a very thin, so especially exciton can be created in the sort of bilayer graphene when Waals heterostructures by confining the electron and hole into a different graphene layers. The two bilayer graphene layers are separated by the balancing insulation layer. It's called a special balancing HBN layer, which are acting as a barrier to separate the electron and holes. Okay. The electron hole can be also equaling number of electron holes can be also created by confining by applying a strong magnetic field, and at the half filling of each Landau level, there will be equal number of electron and holes. Also, in this way, we can sort of create in this way, so when the two layers are two layers are brought very close to each other, the strong like interrail interaction can appear, and which can promote the especially excitons. So the exciton condensate in this system is confirmed or has been confirmed in the quantized hole drag resistance, and where you pass the current in one layer and record the hole resistance in the other layer. And also the vanishing RXX as well. So the exciton superfluidity phase in this phase is is further confirmed by the counterflow measurement, where the zero resistance or zero XX is recorded when a superphase is formed. But the exciton constant phase in this case exhibits some selection rule. The condensate phase is not only observed in the quantum Hall state with total filling factor 1, but also in the electron quadrate. The condensate phase is also observed in those filling factor like 3 and also 5 here, but not in the total filling like 2 or 4. So to understand this selection rule, we need to look back at the zero energy lambda level of bilayer graphene. The zero energy lambda level has 8-fold degeneracy. Although the 8-fold degeneracy lift states has been observed in various experiments, but so far those work to work out the quantum number of each quantum states is limited to the capacitance measurement. But most measurement we are doing is in the transport. So in the following few slides, I will show how we use use transport measurement to determine the quantum states for each quantum Hall like filling factor. Here the device we fabricated. The bilayer graphene is encapsulated by top and bottom HBM. There is a graphite gate at the bottom and a metal top gate. The quantum Hall can be observed around 5 Tesla in this sample, and the lambda level spectrum of the R-axis is highly resolved, as we've seen here. And the lambda level spectrum the line cut of lambda level spectrum is shown in the figure E, where we can see very clear oscillations, and the whole plateau is recorded in F, and again the G is the line cut of the F. We can see very very quantized sigma xy. With the highly resolved lambda level spectrum, we first trace the evolution of symmetry break states in the zero lambda level as the magnetic field increases from 2.5 Tesla to 40 Tesla. And at 2.5 Tesla, the lambda level is nearly degenerate in the zero electric field and split into two in the high electric field. As the magnetic field increases, more lambda level splits out. And at 10 Tesla, we can see a total 8-fold degeneracy has been lifted, and we see so there are total 8 lambda levels here. With high quality sample, we are able to extend our lambda level spectral measurement to a very high discriminant field. So in high discriminant field, we can now see new lambda level, zero lambda level crossings at filling factor 2 and 1 and 3. So as I highlighted by the recircles here, one thing we noticed is that the Landau label crossing in the high issue field or high displacement field shows a very strong electron hole symmetry, where we can observe two crossings at on the electron side, but only one on the hole side. So we try to use a highly resolved Landau label crossing constraint or to the Landau level modeling for determining the quantum number of each quantum hole states. The left side shows the experimental data I just showed in the previous slides, and so if we use a single particle model, the model results are shown in the right side. As we can see, the model works well for the low electric or low displacement field. However, the single okay, so I'm sorry. However, the single particle model can't explain the high displacement field crossing. As we can see from single particle model, we can see only one crossings on the electron side, but there's no crossing on the hole side, which are quite different from what we observe in the experiment. Furthermore, the Landau level being sequence from single particle model is not consistent with from the capacitance measurement. For example, in the Landau level being sequence from single particle model at the zero displacement field is 0.0001111, and but that from the capacitance measurement is a 0.0110011. So inconsistent the inconsistent crossing in high displacement field and the incorrect filling sequence remind us that something is missing in the theoretical modeling. So the previous measurement shows the candidate ferromagnetic to ferromagnetic transition by using independent field. Tell us we might need to include a Coulomb interaction for the modeling. So what we did is we add a simple term in the Hamiltonian or in the single particle model to mimic the Coulomb interaction. So after adding a effective Coulomb interaction term in the single particle model, we now can see now the modeling results qualitatively agree well with the experimental results in both low D and low D and high D fields. And also we check the filling sequence from the theoretical modeling. Now at the zero H field, the filling sequence is consistent with what the people had been observed in the capacitance measurement. So in this work we basically fabricate a high quality bilayer graphene sample, and we are able to extend our measurement of the Landau level spectrum to a high D crossing to the high displacement field, where we see strong electron and hole symmetry and new Landau level crossings. And we use our new observation and to constrain the modeling, and then we can use more sort of accurate model. We can now also correctly tell the fitting sequence, which we can be used to understand the selection rule in the excellent computation in double bilayer graphene quantum wheels. So yes. Finally, I would like to thank people has been provided the collaboration. The works are supervised by Alex Hamilton, and Abe is working closely with me on the experiment, and also he contributed quite a lot in the theoretical calculation with Andrew Charles and Dave Nielsen and Francois Peters and Mirad. And the device fabrication is also in collaboration with Barbaros from NUS, and the boron nitride are supplied by the NIMS team. Yeah. And also this work is supported by Fleet and ARC, and the fabrication is done in AMP. Yeah, thanks.
Alex, do you want to coordinate questions, or if anyone's got a question?
Thank you, Feixiang. Yes. So if anyone's got a question, please raise a hand or just unmute yourself and ask. So, Feixiang, what limits in your experience, what limits the quality of the samples?
So, so I think there are a few limitations. For example, for like a crystal here. So, first of all, like it's very difficult to get a very clean and like 2D flakes, because it's always there are some like polymer residues on the surface, and also it's been difficult to get a large HBM crystals as well. And the other sort of difficulty is the contact. So the technique we are using now is using the edge contact. So it takes quite a lot of time to figure out the right recipe to expose the 1D edge of this graphene. Yeah, like a one-dimensional contact. Yeah, and yeah. So then in terms of the like twistor like tronics or the moiré superlattice, to control the right angle is also quite difficult. Yeah. Yeah. Yeah.
Okay. Do we have any other questions? If not, please give a virtual round of applause to Feixiang. Thank you for the talk. And I look forward to seeing you all virtually in the next few meetings, and some of us at the retreat at the strategy meeting at the end of this year. So thanks very much for attending, and see you soon.